Next, let's think about the energy in the simple harmonic motion. So if we have our mass on a frictionless horizontal frictionless surface attached to a spring with spring constant K, and it's oscillating back and forth, what happens to the mechanical energy as it oscillates? And let's remember that mechanical energy U is the sum of kinetic energy and potential energy. Kinetic energy is 1/2 times mass times the velocity squared. The potential energy is the spring potential energy, which is 1/2 times K times X squared. There are three positions of interest. The first is at equilibrium, or one of them is at equilibrium. That's where X equals 0. And another is at the amplitude. That's where X equals A amplitude. So let's think about the energy in each of these cases. Why don't we start with at the amplitude? So at the amplitude, our total energy is the kinetic. The kinetic energy is 1/2 times m times v squared. Let's think about what happens at the amplitude. At the amplitude, it either switches from moving right to left, turns around, or at the negative amplitude, it switches from left to right. So at the amplitude, it's a turning point. When that happens, the speed is equal to 0. Okay, and you can see that on the graphs we drew earlier as well. So our total energy is the kinetic, 1/2 times m times 0 squared, plus the potential energy, which is 1/2 times k times x squared, but x is equal to a. So the total mechanical energy at the amplitude is 1/2 times k times a squared. It's all potential energy at the amplitude. Okay, next spot we could think about is somewhere in the middle. In the middle, right here, x is not 0 and v is not 0. So the energy has sum of both, 1/2 mv squared plus 1/2 kx squared. So a bit of both there. What about at equilibrium? At equilibrium, x is equal to 0, so there's no potential energy, which means it's all kinetic. So that must be the biggest that the kinetic is, which means that must be the maximum velocity. And that makes sense too. As our oscillator approaches equilibrium, there's a force pulling towards equilibrium, speeding it up. So it gets faster as it goes towards equilibrium. Once it passes equilibrium, there's a force pulling it back, slowing it down. So after it passes equilibrium, it slows down. It means that the velocity is the biggest at equilibrium. So at equilibrium, our energy is kinetic, 1/2 times m times v maximum squared, plus 1/2 times k times x squared, but x is equal to 0 because it's at the equilibrium. So what we have here now is three different ways to write down the energy depending on where we are. But we'll remember that we had a smooth surface, which means that there's no friction. If there's no friction, there's no loss of energy, which means that the energy is conserved. Mechanical energy is conserved. So what that means is that the total energy can be written any of these three ways. So total energy can be given by 1/2 times k times a squared, can be given by 1/2 times m times v squared plus 1/2 kx squared, or it can be given by 1/2 times m times v maximum squared. Those three expressions are equivalent. So anytime you have to calculate an energy, you're allowed to use any of those expressions. You just pick the expression that fits the information you know. Okay, the last thing we might like to do with energy is draw a graph of the energy. Well, let's do potential energy first. Potential energy is 1/2 k times x squared. Potential energy is equal to 0 if x is 0. Since it goes as 1/2 kx squared, it's a parabola, an upside down parabola. So that's the potential energy. The total energy, total mechanical energy is conserved. So that would be a horizontal line. So that's E total. That's a constant value, equals K plus U. So that's a value given by a half KA squared, or a half MV max squared, or a half MV squared plus a half KX squared, all equal. So that's total, and that's constant, given by any of the three terms above. And then the last expression we might put in would be our kinetic energy. So at the amplitudes, our kinetic energy is 0. At the equilibrium, it's the biggest. It goes as a half MV maximum squared. So that also looks like a parabola. So there's our kinetic energy, which is total energy, subtract potential energy, 1/2 mv squared. Conservation of energy gives us a way to verify that the expression for maximum speed of an oscillator is amplitude times angular frequency. So let's just kind of quickly recap and jot down a few notes. Energy is kinetic plus potential, and in general, it will have some of both. Energy is 1/2 mv squared plus 1/2 kx squared. If we're at equilibrium, that's where x equals 0 and v equals a maximum. Then we have energy equals 1/2 mv max squared. And this is a summary of what we did at the previous slide. At the amplitude, that's where x equals a and v equals 0. And that's where our energy is 1/2 Ka squared. If we're trying to find V maximum, we'll remember that energy is conserved and we'll apply conservation of energy. That tells us that all these three terms are equal. So I'm going to set this term equal to this term because they all have to be equal anyway. And this is kind of the two that's the most interesting to me right now. So 1/2 V maximum squared equals 1/2 times K times A squared. Right off the bat, I'm going to divide both sides by 1/2. Then I'm also going to divide both sides by M. V maximum squared equals K over M times A squared. I'm asked about V max. I'm going to take the square root of both sides. V max is the square root of K over M times A squared. Root K over M, that's omega. And root of A squared is just A. So V max then equals omega times A. So that's the same as the expression we got from taking the derivative of our position equation. This is just finding that same expression a different way. This is an example of an oscillator that can be solved using either energy or the equations of motion. I think I'll work through both ways for you, and then you can kind of pick whichever method you'd like to use better for solving problems. So we have a 2 kilogram object oscillating with simple harmonic motion. It's moving horizontally. We have the position as a function of time equation. We know the amplitude is 1.23 meters, and we know the phase constant phi is 0.566 radians. Find the speed, notice that that says speed, not velocity, when the oscillator is 0.615 from equilibrium. Okay, let's tackle this using the energy method first. So what we do is we write down our expression for conservation of energy, 1/2 mv squared plus 1/2 kx squared equals 1/2 Ka squared equals 1/2 mv maximum squared. There's the general overall expression. Which two look good here? I know amplitude. I don't know anything about V maximum, and I don't really care either. So I think I'm going to use my first two terms. 1/2 mv squared, because I want to find my speed, plus 1/2 kx squared, I know my x, equals 1/2 Ka squared. I know my a and I don't know my k yet, but let's see if we can figure that out as we go. The first thing I'll do is I'll divide through by 1/2. Now I'm going to try and figure out my k value. So if I look at my expression up above, x of t is equal to a in general times cosine of omega t plus phi. This shows me that my omega must be 2 pi radians. Those two things have to be the same. 2 pi radians per second. The other thing I know is that omega is root k over m. That means that k equals omega squared m. So I'll put in my omega as 2 pi, I'll put in that my m is 2 kilograms, and I get my k to be 79 newtons per meter. Now I'm all set to finish solving my equation and finding v. So I have mv squared plus kx squared equals ka squared. I want to find my v, so I'm going to take my kx squared to the other side. Mv squared equals ka squared minus kx squared. I'm going to divide both sides by m. V squared equals k over m a squared minus k over mx squared. I can take my k over m outside. A squared minus x squared. And then to get my v, I have to take the square root of the whole thing, k over m, a squared minus x squared. Now I'm a little bit out of space, so let's just see, hopefully I can squeeze it in. K is 79 newtons per meter, divided by the mass of 2 kilograms, times that by a squared, a is 1.23 meters, minus x squared, 0.615 meters squared. Don't forget to take the square root. And what we get for our v is 6.69 meters per second. Careful to notice here that this is speed. It is not velocity. It doesn't tell us which way the oscillator is moving, left or right. It just tells us how fast. Now you can solve this exact same problem using the equations of motion if you wish. So using equations of motion, we know that x of t is equal to 1.23 meters times cosine of 2 pi times t plus 0.566 radians. Okay, it says 0.615 meters from equilibrium. 0.615 meters equals 1.23 meters times cosine 2 pi t plus 0.566. I'm going to divide both sides by 1.23. So cosine of 2 pi t plus 0.566 equals 0.615 meters over 1.23 meters. So then 2 pi t plus 0.566 equals the inverse cosine of 0.615 meters over 1.23 meters. Do that through the calculator. You should get plus or minus 1.05 radians. Now your calculator is going to tell you plus, but you know that it can also be minus. So you can solve for t if you wish. You don't really have to though, and here's why. When I write down my velocity equation, v of t, that's minus a omega sine of 2 pi t plus 0.566. So we know what 2 pi t plus 0.566 is. It's plus or minus 0.105. Okay, let's put that stuff in. Minus 1.23 meters times my omega, that was 2 pi, seconds to the minus 1, times sine of plus or minus 1.05. Okay, what this gives me, if I put in my plus, then I get minus 6.69 meters per second. If I put in my minus, I get plus 6.69 meters per second. Now, the question only asked for speed. This is velocity. So my speed would just be the magnitude of either of those equals plus 6.69 meters per second. So either way you wanted to tackle this problem, you should get the same answer. Okay, let's go through an example now that looks long at first glance, but it shouldn't be too long as we go through it. A 1.5 kilogram object is attached to a spring and placed on a frictionless horizontal surface. So right at the very beginning, there's nothing going on and it's at equilibrium. That's where x equals 0. A horizontal force of 15 newtons is required to hold the object at rest when it's pulled 0.02 meters from its equilibrium position. Okay, so that means we pull it to the right and we have to hold it in place with some sort of holding force. And we know what's happening is that we're holding it, so we're pulling on it to the right. The spring is pulling it back towards equilibrium to the left. So we've got the spring force here. And this is what happens when we pull it out 2 centimeters, 0.02 meters. Okay, then we're going to let it go and it's going to oscillate back and forth. So already we have an idea that the amplitude is going to be 0.02 meters because we release it at 0.02 meters. Okay, let's see what we're asked to find. Find the force constant of the spring. So what we know about a spring force is that the spring force is minus k times x. I'm being careful to write the vector equation here. My spring force is to the left, so it has a direction of negative x and a magnitude of 15 newtons. If my mass is being held still, then the force I apply to it has to balance with the spring force. So my force is 15 newtons, means the spring force is also 15 newtons, equals minus k times the x value, which is positive 0.02 meters. Solve for my k, 15 newtons over 0.02 meters, and I get 750 newtons per meter for my spring constant. Okay, that's part A. Part B, what is the angular frequency? That's asking us to find omega. Omega is 2 pi over the period. We don't know the period. Omega is also root k over m. We do know k and we do know m. So the square root of 750 newtons per meter divided by 1.50 kilograms to get 22.4 radians per second. Okay, that's A and B done. What about C? What is the amplitude of oscillation? Well, we take our mass, we hold it out by 0.02 centimeters, and then we release. So 0.02 centimeters is the amplitude of oscillation. You have to get that part from reading the problem. Okay, new slide for part D. Part D asks us to find the maximum speed of the object. We know that maximum speed is equal to A times omega. We'll put in our A, 0.02 meters. Multiply it by our omega, 22.4 seconds to the minus 1, gives us 0.447 meters per second. At what value of x does this occur? This happens when x is equal to 0, so at the equilibrium. Part E. Find the magnitude of the maximum acceleration. What is the value of x for this? So A maximum is equal to A times omega squared, 0.02 meters times 22.4 seconds to the minus 1, that's got to be squared, gives us 10 meters per second squared. This happens when x is at the amplitude. So the acceleration has a maximum value when x has a maximum value. Okay, that's parts D and E done. What about part F? That wants us to find the total energy of the oscillating system. So total energy we can find 3 ways. We can do 1/2 times m times v squared plus 1/2 times k times x squared. We can do E equals 1/2 m v maximum squared. Or we can do E equals 1/2 k a squared. These 3 expressions are equivalent. It doesn't matter which one we use. I'm going to use the bottom one. So 1/2 times k times a squared is 1/2 times 750 newtons per meter. times the amplitude, 0.020 meters squared, gives me 0.150 joules. So that's the total energy of the oscillating system. Part G, we want to find the speed when we know x. So G kind of naturally follows from part F. In F, we found that the total energy was 0.150 joules. We know energy is given by 1/2 times m times v squared plus 1/2 times k times x squared. X is equal to 1/3 of the amplitude. So x is equal to a over 3, 0.02 meters divided by 3, 0.00667 meters. We know our mass is 1.5 kilograms, and we know K is 750 newtons per meter. So we're trying to solve for V. So 1/2 mv squared equals E minus 1/2 kx squared. Divide both sides by 1/2 m. And then we'll take the square root of everything. Now, I'm not going to go ahead and write in the numbers. 0.422 meters per second is our answer. Hopefully you notice here that this v is smaller than the maximum velocity, as it should be.